Welcome to week 6. This is part A of week 6 lesson. Today's objectives. Students are going to learn how to determine the gravitational potential energy of an object. Gravitational potential energy can be thought of as the energy stored in an object. Energy stored in an object due to its position above the Earth. Let's go ahead and review what we did last week. So go ahead and get out your notes from last week. Let's go through them real quick. Last week we were talking about work. Remember, work is capital W. Work is measured in joules. It's one way that energy can be transferred from one object to another object by doing work. And work has to have two things. It has to have force and distance. Newtons and meters. You multiply them, newtons times meters. And we use an example of lifting a bucket of water out of a well. You do work when you lift a bucket of water out of the well. I think everyone realizes that. The amount of work done is the force is the weight of the bucket, which is m times g. Weight, calculate. How do you get your weight? Mass times 9.8. That's the weight. Force. And then the distance is how high you lift it out of the well. So h, mgh. This is the work done to a bucket when you lift it out of the well. We're going to come back to that today. This week we're going to be talking about different forms of energy. So in general, what is energy? We use the capital letter E, and it's measured in joules, just like work is measured in joules. What a coincidence that is. And energy is the ability to do work. The more energy you got, the more work you can do. So we're going to see how this all comes together starting today. So let's try an example like this. How much work is done to lift this boulder right here? So here's a boulder. It was on the ground. We lifted it 5 meters, and the boulder has a mass of 200 kilograms. Let's talk about the equation for work. Work equals force times what? Distance. It's force times distance. So you can figure out the force times distance, but we can also put it in terms of 3 different letters that are related. So first, the force, we put these 2 letters together for the force. The force is the mass times something. Weight, calculate. How do you get your weight? Mass times what goes here? Little g. All right, so that's the force. The force is the weight. Mass times 9.8. Now the distance. What's the distance here? Another way we can talk about the distance is this. It's the height. It's the height that you lift the boulder. The distance is the height. So these are kind of similar things. Force is weight. Distance is height, so work is weight times height. So let's go ahead and plug in our numbers now. Just plugging in mgh. So what goes here for m? 200 kilograms is the mass. What goes here for g? 9.8 is little g for Earth. And then what goes here for h? 5 meters is how high we lifted it. If you multiply these all together, 200 times 9.8 times 5, you end up getting 9,800. 200 times 9.8 times 5 is 9,800. What's the units for work? Work is measured in joules. And energy is also measured in joules. All right, so let's think about this. Before the boulder is lifted, it seems to have no energy, right? Just sitting here next to Bunny, not doing anything. It's not moving, just sitting still. Doesn't have any like chemicals in it. It's not to cause any fires. There's no like electricity coming out of it. It makes no sound. It's just sitting there. Basically no energy sitting there next to the bunny. But then we lifted it. This is something different, right? I mean, it's still sitting there. It's just, if you hold it, you lift it and hold it, it's just sitting there. It's still not moving. It's not catching fire, nothing. But there is something different about this when you lift something, right? When you lift it, let's look at this. Here it is on the ground, no energy. Then we lifted it. This is a little different now because what do you think happens if you let go of it? You let go of it, it has the ability to do something, right? It's going to fall. Oh my gosh. You lifted it, let go of it. This is different now. This right here is different than what it was before, just sitting here. Obviously, something has changed. Just by lifting it, and now when you let go of it, this is different. The rock, the boulder did work on the bunny, right? It applied a force, a crushing force through a distance of the bunny and did work on the bunny. Not only that, but when it fell, it did work on the Earth, right? probably left like a little crater on the ground. It smushed in the ground, did force and distance, and did damage the earth, work done to the earth. There's also other forms of energy that were released when it fell. Sound waves, right? I mean, a crashing sound. And waves are energy. And there's another type of energy which you might not realize, but also infrared waves, heat. It gave off heat. It kind of warmed up the rock and the ground a little bit, and the bunny. It warmed them up when it hit. So infrared waves, all these forms of energy, they're all measured in joules. All these forms of energy came from somewhere, right? It didn't have this energy, these forms of energy before when it was just sitting here, but it got this energy from when you lifted it. Before, none of those forms of energy were there. And now after you dropped it, all these forms of energy. Got those energy when you lifted it, okay? So when this boulder is dropped from this height, how much energy will be released? Released after you let it go. When I say release, it means went out into the air, into the ground, into the bunny. Well, we know the amount of work we did was 9,800 joules of energy, like stored in there. And then we let go of it, all the energy came out. So that energy release is going to probably be pretty much the energy that we stored in it. Let's talk about this. When we lift objects using work, there's energy stored in the object in the form of what we call gravitational potential energy. Gravitational potential energy. So let's think about these three words, okay? Gravitational potential energy. Let's first talk about potential. What do you think the word potential means? For example, when someone says that you have potential, what does that mean, to have potential? Well, to have potential means you have the ability to do something. The potential to do something. Does it mean that you're necessarily doing it? No, you might not actually be doing anything, but you have the potential, the ability to do something. Now let's talk about energy. What does the word energy mean? We already talked about energy as the ability to do work, the ability to do work. And then finally, what does the word gravitational mean to you? Why did we use the word gravitational for this picture right here? Well, it has to do with gravity. If there's no gravity, then there would be no energy stored in this. It would just be a rock floating out in space. So gravitational potential energy, put all three of these together, and that's what you have. Gravitational potential energy, you have energy stored and the ability to do work because the object is in the Earth's gravitational field. So let's kind of get this in our notes. We had this before. Here was work, mg times h, and the bucket, and ability to do work. Potential energy. Gravitational potential energy, joules, is the energy stored in an object because of its position above the Earth's surface. And then potential energy, PE, is equal to mgh. M is the mass in kilograms. G is little g of the Earth's 9.8 meters per second squared on Earth. You can get that from your yellow formula sheet. And h is the height above the Earth that you lift something up. So let's go ahead and get that in our notes. Alright, so kind of putting together what we had from above, the work done to lift the bucket of water was stored as its potential energy. So they kind of go together. The force times the distance that you did for the work, the newtons times the meters, equals mgh, the weight times the height, meters, newton meters. So that's how they are both work together, both newtons times meters, and this is the work done to lift something, and this is the energy stored when you lift something. So they're very similar equations. So let's go ahead and copy that in our notes. Okay, so let's finish up today with a warm-up example of calculating these. So turn your page to a blank page. Warm-up 4. copy the blue on these. We're going to do 2 examples. This mannequin has a mass of 50 kilograms. And what is the gravitational potential energy halfway up the stairs? When the mannequin goes halfway up the stairs, what's the gravitational potential energy? Then we'll figure out all the way to the top of the stairs. Okay, so let's do halfway up the stairs. So here's our copy of the blue. Here are givens, and the unknown is going to be potential energy. This is the equation, GUE, and then S is substitute, and then S is solution. So let's first do the givens. What goes here? What is the mass? 50 kilograms is the mass of the mannequin. What is little g? 9.8 meters per second squared is little g. What do we put in for h? The height, when the mannequin walked halfway up the stairs, it walked up 2 meters, so that's the height. Then we have our equation, potential energy is m times g times what? What letter goes there? H. So now we just plug in, use this like a recipe, and plug these numbers in. What goes here? M is 50 kilograms. What goes here? G is 9.8. What goes here? H is 2 meters. So 50 times 9.8 times 2, you put that in your calculator, multiply it all together, and you will get 980. What are our units for gravitational potential energy? Joules. The units for all types of energy is joules. All right, so there's our example. It has 980 joules of potential energy. So if the mannequin kind of steps off the stairs here, he'll fall, and then when he hits the ground, 980 joules of energy, mostly in the form of work done to the mannequin when the mannequin hits the ground, and maybe some sound. So what about near the top of the stairs? What's the potential energy going to be of the mannequin when it's standing at the top of the stairs? So we'll do it again. Givens, unknown is potential energy. There's the equation. Substitute, solve. G-U-E-S-S. Okay, just follow this example up here. So what are we going to put in this first row? The mass is still 50 kilograms. It's the same mannequin. What goes here? Little g is 9.8 meters per second squared still. What goes here? Height, h is now 4 meters because the mannequin climbed all the way up to the top of the stairs, so it's 4 meters up. Then we plug in our numbers. What number goes here? M is 50. What number goes here? G is 9.8. What goes here? H is 4. 50 times 9.8 times 4. Well, let's see. Since the mannequin walked up twice as high, it was 2 meters here, now 4 meters, probably going to have about twice as much work or twice as much potential energy. So when we multiply this together, we get 2,000 joules, which is twice of 980 joules. So big picture, overall, what you see is this mannequin has potential energy. When it has halfway up, and if it falls, it can hurt himself. And if it goes all the way up here, it's got twice as much potential energy, twice as much potential to damage himself in this fall. So make sure you have all this copy of the blue. Before we wrap it up, let me kind of go over the word potential energy, the term potential energy in general. So we already talked about when you lift something. Here's a boulder on the side of a cliff. It was lifted up off the ground a certain height, right? And the boulder has a weight, m times g. So the potential energy, the gravitational potential energy is mgh. And that's got a lot of potential energy, right? Because it's probably a lot of mass and pretty high up, and you just give it a little push and it'll fall and do work when it hits the ground. So that's potential energy, gravitational potential energy. But there's other types of potential energy that I just want to mention here. For example, this gal and the bow and arrow, right? When she first picked up the bow, the string was like this, okay? But then she put an arrow in it, and then she had to pull the arrow that way. She had to pull the arrow, and it took force to pull against this string and stretch and, change the shape of the bow and pulled on it. Force, and then she had this distance. Here's the distance she pulled, right? The distance. So force and distance. So she did work to this bow, And now there's energy stored in the bow, right? And if she lets go, it'll launch that arrow. Potential energy in the bow. That's not gravitational potential energy, which is not in our equation. It's a different kind of equation, but it's still work done to the bow, potential energy. Let me give you one more example. Would be, let's say I had a spring, okay, and then I had this book attached to a spring, okay, and then if I were to pull on it, it stretches the spring, stretches the spring, stretches the spring, right? The more I pull on it, that's the distance, okay, and the force. It actually, the more you pull a spring, the more it stretches, the harder it is to pull, okay? Eventually you get to a certain distance where it's hard to pull, but you get the idea. You're doing work on that spring, and now there's energy stored. And what do you think happens when it lets go of the book? It'll pull it back this way, and maybe it'll crush the spring, and then maybe start oscillating, but basically it'll give it motion. All three of these are examples of potential energy. This one's gravitational potential, and this is potential energy stored in a spring and in a bow.